All right, this is going to be a continuation of the Ethernet lecture from last week, and I'm coming to you live from the bright and sunny Florida shores. Having gotten off a little early today, I'm glad that I can actually record at least the first lecture for this week. And today what we're going to do is going to wrap up the Ethernet introduction. We're going to talk about spanning tree. We're going to talk about how switches learn addresses. We'll talk a tiny bit about design. And so hang with me, and I do apologize for the way this is having to be delivered, but hey, we're doing the best we can. So let's see if I can get this to go. There we go. First thing we want to talk about is something called the spanning tree protocol. Ethernet is a protocol where you throw your packet out there. You're a network interface card. You've been asked to transmit a packet. You just drop it on the network, and it goes. Everybody is supposed to be able to receive it. So if you're connected to a switch, let's see here, we'll bring up my trusty pen here. If you're connected to a switch, you're connected, here's somebody else, here's a third person, maybe here's a fourth person. And you send a packet into that switch. I'm going to change pen colors here. You send a packet in. What the switch is going to do is, just like any bridge, it's going to look at the destination address. That packet will be destined for one of these two. Maybe this is node 1, 2, 3, and 4. And so you're trying to send it to node 4. Well, if the switch doesn't know where node 4 is, the switch has to broadcast it. He has to send it to everybody. He has to basically emulate an old Ethernet coax cable where everybody communicated with everybody all the time. So if the switch doesn't know yet where that's at, he'll just send it to everybody. Well, that works great, except what if I have another switch up here and a third switch right here? Boy, I'm running out of space. And I've got these guys in kind of a loop. And none of them know where 4 is. Well, guess what's going to happen? Go back to a orange. Orange is a bad color. This guy will forward the packet there. He doesn't know where it is. He'll forward the packet there. He doesn't know where it is. He'll forward the packet there. He doesn't know where it is. And they will just continue to go round and round and round and round. This is known as a loop storm, and if you send a broadcast packet, there's no choice. Every broadcast packet has to be delivered to every port, and if you do a broadcast, let me erase this thing. I think I can get rid of it without losing too much. There we go. If you do a broadcast packet, that packet has to go out there, it has to go out there, it has to go out there, and it has to go out there, and that packet here will be broadcast there. The packet there will be broadcast back to the original switch, who will send that broadcast packet to everybody, including the original sender, and will send it back around to the other switch. And this is known as a broadcast storm. And these are very bad. And the reason they happen is because we have loops in the network. Ethernet does not handle loops very well. I'm going to get rid of these extra switches and go back and get a pen here. And there's my switch again. All right, very good. All right. So what we have to do if we have a loop in the network, we actually have to choose one of these guys to become the root, and we're going to convert this guy into a tree. And if you remember from math or computer science, a tree is an arrangement of data or nodes or whatever, and none of those there are no loops in this. There is no path that loops around. So if I've converted the configuration above into the configuration below, actually this link right here is, I'm going to dotted line it in there. This link is still there, but what these guys down below are going to do is they go, hey, we're not allowed to have a loop, and one of them will stop listening or stop transmitting. He will put that into a shutdown mode. All right. So, and what that will do then is it will say, if this guy right here has to broadcast, he can broadcast there and there. This guy can broadcast that way and that way, but this guy can only broadcast there. He's not allowed to transmit this way, and this kills the loop. And this guy will also not receive that way because he's put this into a disable mode. Now, if he senses that our node over here loses this link, he'll start talking on that link again. Boy, that's a big mess. So let me get rid of this, get rid of all this stuff. Yeah, that's good enough. Yeah, all right, we got a few extra dots on there. So We handle loops by having this thing called the spanning tree protocol. In this protocol, every node transmits, let's see if I can get a highlighter here. Every node transmits to his buddy that, hey, I'm a node and here's my number. And they basically pick the node with the highest number to become the root. And then all the rest of them say, they turn on their links that get them towards the root, and they might turn off links that leave them not connected to the root. And in the end, they will build a tree, and that tree will prevent loops. Now, you should go, I've got this YouTube link on the bottom here. I'm going to highlight it. Da, 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 da. No, I'm not. There it is. Right down there in the bottom. You should go to that loop. Professor Messer is a great resource. If you haven't used him before, you should bookmark him or subscribe to him or something. He's done videos on all kinds of tech, and he has a great Professor Messer on spanning tree, talks about how it works, and you need to go take a look at that, and that'll give you an idea of how this works. All right, so now let's talk about how we learn. I've got a network over here with just 3 nodes, A, B, and C, and here's a switch. Now the switch has a forwarding table. Ooh, that's really ugly. I do not like that pen. How can I change that pen? Oh, because it's a highlighter. I want to, no, I don't want a laser pointer. I want a pen. Aha! All right, so I have, oh, now it's a red pen again. Oh, well, that's okay. There's no destiny here. This is not a red pen of destiny. The switch is going to have an address and a port. Oh, this is really hard to read. Now, I'm going to go, that's 1, 2, and 3. So node A is on port 1, node B is on port 3, and node C is on port 2. Now, you have to remember what an Ethernet frame looks like. A frame has a destination address, there's a D, a source address, and a type, and then it has a bunch of data after that. So let's say this switch has just booted, nodes A, B, and C are ready to go, and node B needs to send a packet or a frame to node A. And so what node B will do is he will send that frame, and the switch will receive it. The switch is transparent. Node B doesn't know that he's talking to a switch. The switch will say, okay, I've got to deliver this to node A, to destination address A. He looks in his table. This is the address, and he goes, hey, my table is empty, so he has to flood it. And so what he does is he sends that packet out port 2 and port 1. He does not send it out 3 because he received it from port 3. Now he does look, he says, you know what, I just heard from a node with an address of B, and that node is on port 3. So he adds that node to his forwarding table. Okay, now C receives this message that's destined for A and throws it away. And A receives the message, checks to see if the MAC address matches his own MAC address, and goes, hey, that's my frame. And he does a little work and he says, I'm going to respond. So A sends a packet back to the switch, and the switch looks at the destination address and says, the destination address is B, and he looks down here in the table and he goes, hey, I know where B is, and he only sends it out port 3. He does not have to send it everywhere else because he learned previously when B transmitted where B was connected. Now when A transmitted this, he also learned where A was connected because the source address would be A, the destination address would be B, and there'd be some type in here. So now he says, hey, my node A is on port 1. All right. A little later on, C decides to send a transmission, and C sends a transmission to B. So I've got another frame here, and the destination is B, and the source is C, and there's some type. Now when that happens, the switch says, hey, you know what? I just received something from C, and C is connected to port number 2, and now he has a full forwarding table. Whenever he now receives a frame from any of these, he will be able to go into his forwarding table and figure out which port to send it to, and that's the only place he'll send it. So other people won't see it. So I've walked you through this, and I'm going to erase everything on here, erase all ink on the slide. And now let's walk through what happens when you receive a frame. So first of all, step one, let's get this back up here. Let's do a different color. Let's do kind of purple. Step one, right here. When the frame arrives, let's go back. B is sending a frame to A. He wants it to be delivered to A. The first thing that switch 1 does is he says, hey, I just got a, here I'm going to draw this again. There's my frame. The source is, the destination is A. The source is B. There's some type in there. Switch 1 says, you know what? Step 1, I record the link associated with the sending host. B just sent me something, and B is on port 2. And he records that in his table. He then looks in his table. If he finds A in the table, you can see A is not here right now. If he finds it, he sends it out the port. Otherwise, he floods it. So what he's going to do right now, he's going to do this else. He's going to send it out everywhere. He sends it out A to port 1 and to port 2. And, I'm sorry, I changed that up on you. Nice. Alright, so that's how that works. This has already been an 11-minute lecture. This is a slightly more complicated thing. Alright, so he flooded it. Now A sends one back, and again, the switch records the link. So he now knows A is on 1. Now he checks his destination. Hey, I found B, and I can send it out there. I don't have to forward it. So this is how it learns. And so you have to kind of combine these things. Alright? Okay. So I'm going to, on the next slide, hang on, I may have a summons to supper here. Anyway, I did get summoned to supper, but I'll finish this first. Alright, so I'm going to draw 6 switches. I'm going to draw 1 or 2 hosts on each switch. The forwarding tables are empty. These are all on the next slide. And now we're going to say what happens if one node sends to another. First thing we're going to do, though, is we are going to assume that we need to build a spanning tree. See, we've got all kinds of loops in here. So what happens when we build a spanning tree? These guys all look and they elect a root. The root is going to be the lowest number. So I'm going to circle the root in purple here. The root becomes 1. All right. Now, node 2 says I'm going to keep this link alive between, I'm going to go to red so we can actually see this. Node 2 says I'm going to keep this link alive from me up to 1. Node 4 says I'm going to keep this link alive. Now, between node 2 and node 4, there's a link. One of them has to talk to that link because there could be stations on that link. It might be an old style Ethernet coax. We don't know. One of them has to maintain a link. Which one maintains the link? Notice this link right here is 1 hop away from 1. It could go through 4 to 1 or it could go through 2 to 1. The way they decide is the node with the lower root ID, and so this guy's ID is 2, this guy's ID is 4. The guy with the lower ID will actually be the one who keeps the link open. So 2 says, I'm going to manage this. 4 says, I'm going to turn this off. All right? And so now 2 owns this link. 4 does not talk on this link anymore. Now 3 says, okay, I've got to pick a path back to the root. He could go this way through 4, or he could go this way through 2. And he gets the ID from both of these guys, and he goes, you know, I'm going to use the one that has the lowest number. So he's going to go up here. His path is going to be up through 2. So this link stays open. This link over here needs to be shut down. So who actually gets to continue using this link? It's actually going to be the port that is closest to the root. The root is up here. I'm going to put a big R there. This port is closer to the root. You can see it's up there. So 3 shuts that down. I got to go back to red. So 3 shuts that down. Let's go back to 5 now. 5 could go down here and then up through 3 and 2 to get to the root, or he could go directly through 2. He says, you know what? It's faster for me to go that way. So this link stays open. Now, this link here in the middle that I'm circling is equidistant. It's 1, 2, it's 1, 1, could go through 5 and then 2, then 1, or it could go through 3 and then 2 and then 1. And the node that's going to support it is the one with the lowest ID. So 3 keeps this open. I'm circling that right there. And 5 turns this port off. So now anybody that's on this link, if there were a couple of people somehow on this link, maybe through an old style hub or something, their path back to the root would be through 3, then through 2, then through 1. All right. Now 6 goes, you know what, I have 2 paths all the way up to the root. And what 6 does is going to choose the path that goes through the lowest numbered ID. So this link stays open. 6 says we got to shut this one down. This one over here is going to go down. One of these two has to close. 6 closes because he's the furthest away. So now the new tree looks like this. 1 is the root, and he's connected to 4 and 2, and 2 has a single LAN that would kind of go towards 4, but right now 2 just owns that. 2 has a link to 3. 2 has a link to 5. Okay. Now 3 has a link to 6. I made a circle there. Sorry. 5 has the link between 5 and 6 is connected to number 5, and I think that's all of them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 links. 1, 2, 3, 4, 5, 6, 7. I'm missing a couple. 6 should have 1 link. 5 should have 3 links. Oh, no. 3's got a link. The link between 3 and 5 is also open. So there it is. So this is what the tree looks like. There are a couple of links that don't seem to go anywhere, but they have to be maintained. All right. So now let's do an example where nobody has anything in their tables yet. And computer F down here is going to try to talk to computer G. First of all, what's the path? F is off of 4 and G is off of 3. So here's G right here. The path is 4, 1, 2, 3. But none of these guys have anything in their tables yet. So F sends the frame from F to 4, and 4 receives the frame and he floods it. He sends it out that link, and he sends it out to 1. He also learns where F is. He says, hey, this is going to be his link port. Oh, shoot. Back up here. Oh, come on, back down. Let's make this port 2, okay? So now switch number 4 knows that node F is on port 2. He then floods this, and it goes out here. It does not go on the link between 4 and 2. It goes up to 1. 1 repeats the process. But let's call this link 1 and link 2, port 2. Now, node 1 up here also is going to put in his table that he knows where F is. For him, F is out port 2. He floods it, and node 2 says, hey, I just learned where F is. That's 1, 2, 3, 4, 5. For me, that's on node 1, and he literally floods it everywhere. So it's gone up here, it's gone up to 1, and now it's come back down to 2. And then he sends it down to 3. 3 eventually floods it here. But every single switch is going to see this frame. It's going to be flooded everywhere, and everyone's going to learn where F is. Now, they're all going to have their own unique table, and so the numbers may be a little different, but now everyone knows where F is. If H tries to talk to F, here's H over here. 6 knows that the path to F, here's 6. 6 will know the path to F is to 3. 3 will know the path to F is up to 2. 2 will know the path to F is at 1, and 1 will know to send it to 4, and 4 will be able to send it to 2. Notice that it won't be flooded, so 5 will never see that packet from H. So 5 won't know where H is, but because of the way the protocol works, 3, 2, 1, and 4 will also add, G to their tables. So that's how they learn. This is a very quick example, very gross, very ugly. I'm going to try to give you a homework example because there is a fairly large point problem on the exam in a couple weeks that you're going to have to do, where you're basically going to have to do all this stuff. All right? Okay, so let's go on. Here is a situation where we've got hosts connected to a switch, and all we're trying to say here is that it appears as if the hosts are all directly connected to each other. In fact, they are not. In fact, they are only connected to the switch, but the protocol makes it look like they are. Notice that there are no collisions here because they each have their own dedicated UTP. So you can interconnect these switches together like it's drawn here, and the way you should always do it is in a hierarchy. Do not do a daisy chain. Do not do this. Please never do that in any network you design. This is awful. Because if this node goes down, your network's divided. Now I get it. If that node goes down, you still have a single point of failure. There are ways to avoid that. We're not going to worry about them here. But this is terrible, this thing down below. All right, so you interconnect them together in a hierarchy as shown here. And so what's the summary of this? Man, this is a 20-minute lecture. Remember what repeaters were. They were non-intelligent, electronic only. They cleaned up the electrical signal and repeated it. Hubs are basically a multi-port repeater. Basically, they were a repeater that connected lots of cables. A bridge is a layer 2 device that is intelligent and divides collision domains and has a table for forwarding. A switch is exactly the same as a bridge, but it's implemented in hardware. And that's the end of that. All right, so, VLANs. Sorry, I'm not quite done yet. I'm going to draw this real quick. Very simple example. Imagine you had a switch and it had a bunch of users on it. Now these users over here are part of the orange department, losers. These users over here are part of the red department, clearly winners. All right, and these two departments aren't supposed to be connected to each other. So what you can do is you can say to the switch, hey, I want this port, this port, this port, this port, and this port to be red ports. Or you number them, you give them a number. I want this port and this port and this port to be orange ports. Or you could give them a number. And what this switch will actually do is it will create an orange forwarding table and it will create a red forwarding table. And it will never forward from red to orange, and it will never forward from orange to red, just like in the real world. And so it basically sets up a situation where it divides the ports into groups, virtual local area networks. If you want to connect between these two, you have to have a router. And you actually have to, unless the switch supports layer 3 routing, you actually have to put a router in and connect it to two different ports on the switch, and the router becomes a router routing from one LAN, this one down here, to another LAN, this one over here. And so this goes back to that same thing that I told you about earlier. Let's erase everything. Where this is very important to remember. We have layer 1, that's the physical layer, and those are divided by switches. Okay. If you have two switches and you need to divide them, here's a switch, you divide them with a layer 3 device, a router. So routers, which are layer 3, can divide layer 2 devices. Layer 2 devices can divide the physical layer. Okay, hopefully that makes some sense. And basically what happens is you can stick a little header in here and it will tell what VLAN that's on. That's if you're going between things. Don't worry about that too much. I'm not going to ask you about it. All right, what about design principles? I'm going to do this in a different lecture. This lecture has gotten too large, and it's going to take my computer a while to build it. So we're done with this lecture. I'll do a different